Hello everyone. So this is lecture 26 of our subject digital system design, and the topic for today's lecture is logic families, ECL and CMOS. So in our previous lecture we have already covered the performance characteristics of various logic families, their introduction, and then we covered the first logic family, that is the TTL, transistor logic. Now we will be extending this logic family concept to the next two families, ECL and CMOS. So let's start with the ECL family. Okay. ECL stands for emitter coupled logic. The output of ECL provides OR and NOR functions. Okay, like the NAND gate was the basic function realized by the TTL. Similarly, if we ask about ECL, then ECL offers us OR and NOR gate, and again we can see that NOR is a universal gate. We can realize all other gates using that NOR concept. Okay, so each input is connected to the base of the transistor. So in TTL we have seen that inputs were connected to the emitters of the transistor, but in case of ECL family the input is connected to the base of the transistor. Okay, so the circuit consists of three parts: differential input amplifier, then temperature and voltage compensated bias network, and emitter follower output. So these three things we will mark in our ECL circuit in our next slide. So there are basically three parts: differential input amplifier, compensation network, and emitter follower output. Okay. So the emitter output requires a pull down resistor for current flow. So we will be using a resistor at the emitter output to make the output low. Pull down means for connecting the output to the ground level. Okay. In this logic family we consider logic 0 as minus 1.6 volt and logic 1 as 0.8 volt. So these are some denotions of the high and low levels. Okay. So now let's cover to the actual circuit of the ECL logic family, in which we will be first marking these three: one, then compensation network, and third emitter follower output. So this A and B is the differential pair, and then this diode arrangement is the compensation network, and this is the emitter follower output. Emitter, another emitter. So these are my third section of the circuit. Okay, so 1, 2 and 3. Now let's start with the operation. Before coming to the operation, we can see that these inputs are entering the p type base of the NPN transistor. Okay, let's mark them as NPN, NPN, and this one as NPN, also this one NPN, then this one is also NPN, and then this one NPN. So we have to remember that same thing. If the transistor will be conducting, emitter potential will be high. If transistor is not conducting, collector potential will be high. Okay, if transistor conducts, I am again summarizing, if transistor conducts, emitter potential high, and if transistor does not conduct, then collector potential will be high. Okay. So let's start with the case A is equal to 0, B is equal to 0. That means if both the inputs are 0. So if both the inputs are 0, A is equal to 0, B is equal to 0, that means both are low. So this we can see that the low inputs are connected to the P base. That means these transistors will be reverse biased. So that means this Q1 and Q2 will not be conducting. So if these are not conducting, then the emitter potential must be low. So if low, this emitter potential will be low. So if this low value is applied at the N side, then this Q3 must be on, then this Q3 will be on. Okay. Now if this Q3 is on, then its collector potential will be low. Okay, and this will be and this must be, if collector potential is low, then you can see that this is low, then this low is connected to the p type base, then this means this will be off. And similarly you can see that this Q1 and Q2 are not conducting, that means this collector potential, this must be high, this high is applied here, this high is reaching the this p type base, that means p is connected to high, that means this will be on. So Q6 is on and Q5 is off. So if Q6 is on, then this makes a path towards the VCC, that means VCC can be connected to the NOR output. Okay. Similarly, this transistor is off. If this transistor is off, then we can see that VCC cannot reach here, so this output can be connected to ground. So this is the ground side. So this OR output will be low and NOR output will be high. So for this A is equal to 0, B is equal to 0, Y OR is equal to low and Y NOR is equal to high. Okay. So this should have been the case. So this is the operation of OR and NOR's first case for the ECL logic family. Okay. So now let's proceed towards the remaining parts. So if A is 1, B is 0, A is 0, B is 1, and this is A is 1 and B is 1. So for that means if any of the input is high, that means at least there is one input which is high. Okay. So whichever is high, if this is high or this is high, then this particular, this will be, again we are marking as NPN, 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 then NPN, NP and N. Okay. It is a part of a compensation network, so we are not marking anything on this one. So we will not be interested in the conduction of this transistor. So Q1, Q2, Q3, Q4 and Q5. Sorry, Q1, Q2, Q3, Q5 and Q6. These 6 transistors will decide the on and off states of this particular gate. So if any of the input is high, then either Q1 or Q2 or both will be conducting. Okay, whichever is high. So if this is high, that means this point will definitely be at low potential, because if any of the transistors conducting, then if transistor conducts, then emitter potential becomes high and collector potential becomes low. Okay. Then this high value is connected to the N type emitter, that means this Q3 transistor must be off. Okay. If Q3 is off, then this collector potential must be high, because it is not conducting, its collector potential will be high. Similarly, these transistors are conducting now, because it was conducting, that's why this was high and collector potential was low. So this low point is connected to the P type base of this transistor. So this must be off, and this is high connected to the P type base of Q5. So this must be on. Okay. So this Q5 is conducting, Q6 is not conducting. So if Q5 is conducting, that means this prepares a path for VCC connection, that means OR will be getting VCC, and there is no, this Q6 is not conducting. If this is not conducting, then this can be connected to ground only. So that means Y NOR, this terminal will be connected to ground. Okay. So we can summarize as, if A, B are 0, 0, 1, 1, 0 or 1, 1. That means if any of the input, any one of the at least input is high, then in that case my Y OR will be high and Y NOR will be low. So this completes the entire truth table for the OR and NOR gates. So in this way this ECL family is operating. And now let us come to the characteristics. So if you want to summarize in the form of truth table, you can simply mention the basic truth tables as well. Y OR and Y NOR. Okay, 0 0 0 1 1 0 1 1. So OR will be this one and NOR will be this one. So this thing is already covered here. For these three cases, for the last three cases, OR is high, NOR is low, OR is high and NOR is low, and this we have covered in our previous slide. When both the inputs were low, then OR produced a low output and NOR produced a high output. Okay. So this is ECL logic family. Now let's come to the characteristics of ECL logic family. So these are very fast switching with typical propagation delay of 360 picosecond. Okay. So this picosecond delay is very much less, so it is the fastest. That's why ECL family is considered as the fastest logic family. So it is based on bipolar transistor but removes problems of storage time by preventing the transistor from saturating. So transistor are not getting saturated, so it saves up some time, because when transistor enters into saturation and then starts conducting, it takes some time. So this saturation problem is avoided here, so that's why it is the fastest. So very fast operation, propagation delays of 1 nanosecond or less, high power consumption, perhaps 60 milliwatt per gate. So this is a problem, this is a real problem. So if my requirements are such that I cannot afford this much of power dissipation, then I cannot use ECL logic family. Then low noise immunity, this is another drawback. TTL was offering me a 1 to 1 point something logic noise margin, but this is up to 0.25. In TTL it was 0.1 something. Okay. So higher the noise margin, it is better for me. In TTL was offering me higher noise margin. That means I can accommodate 1 to 1.6 of variations. But here noise immunity is quite low, so my variations must be in this range only. Okay. Then used in some high speed specialistic applications, but now largely replaced by high speed CMOS. So in current situation, these are replaced by high speed CMOS, high speed sub family of the CMOS logic family. Okay. So these are the basic characteristics of the ECL logic family. So with this we come to the end of ECL part. Now let's switch to the CMOS. Okay. So CMOS transistor of MOS technology are field effect transistor called MOSFETs, and most of the MOS digital ICs are constructed entirely of MOSFETs and no other components. So it is the best part. That's why these transistor will be taking very less space, because if resistors are used, then these resistors takes very precious space on when we are fabricating the ICs. But in case of CMOS families, there will be no resistors, that means there will be no passive components, so we can save substantial space. Okay. So that's savings are due to this MOSFETs. So most of the MOS digital ICs are constructed entirely of MOSFET, no other components, and MOSFETs are relatively simple and inexpensive to fabricate, small and consume very little power. So there are presently two types of MOSFET, depletion and enhancement, and we will be interested in enhancement type MOSFET. Depletion type MOSFET will not be using. And further, if we see an enhancement depletion, so we will be using enhancement, and in further in enhancement type there will be PMOS and there will be NMOS. Okay. So this is N channel MOSFET and this is P channel MOSFET, and this channel is deliberately shown broken. Okay. Sorry, source to drain. So this will be the flow. So this channel is not there actually, but this channel will be prepared. That's why it is termed as enhancement. That means channel will enhance when we will apply appropriate gate voltage at this terminal. So the applied gate voltage will help in preparing that channel from source to drain. Okay. Similarly here as well, in P type channel as well, The only thing is the gate, whether the gate is of p type or n type. Okay, sorry, the channel is of n type or p type, the gate will be of the opposite type. So in this n type channel, this channel will be of n type and this gate will be of p type, and this p type MOSFET, the channel will be of p type and gate will be of n type. Okay. So we can also see that if we want to conduct, then they have to be forward biased. That means P has to be connected to high voltage and this N has to be connected to low voltage. So we can summarize that NMOS, for NMOS gate should be high, and for PMOS gate should be low. Okay. So this we have seen in form of, because actually this P and N are not the gate, these are the channels. Gate are of the opposite type. Okay. So in a NMOS gate is of P type. Okay. In NMOS the gate is of P type, that's why we are connecting high voltage to that, and in PMOS gate is of N type, that's why we are connecting low voltage to it. Okay. So this is another switching type operation of this NMOS. So this is NMOS type, and NMOS we are applying is 0 volt. So NMOS gate is of P type, I have already discussed. So we are applying a 0 volt to the P, that means it is a reverse bias situation. In this reverse bias situation, you can, sorry, this is a NMOS. NMOS gate is, okay, NMOS gate is P. Fine enough. Okay. NMOS gate is P type, so we are applying a 0 volt at the gate. 0 volt at the gate, that means it will be reverse bias. If it is reverse bias, then this 10 raised to power 10 kilo ohm high resistance. High resistance, that means output must be, it must be off, so that output is low. Okay. Similarly, if you are applying a high voltage to P type, so this will offer a low resistance. Low resistance is there, so it will be on. So it will be on. So this prepares the circuit for this NMOS type. Okay. So 0 off, low off, 5 on, high on. Okay. So this is analogy, and similarly we can do this for PMOS switch. So this for PMOS we can check that the gate will be of N type. Okay. So gate is of N type. Now we are connecting 0 to N type. This prepares the forward bias arrangement. Okay. So PMOS gate will be of N type, and we are connecting 5 volt actually. This is not 0, this is actually 1. This is high because we have applied 5 volt. So high is applied to the N side. So if you are applying a high voltage to the N side, again high resistance due to reverse bias will be generated. That's why it will be off. That means if we apply high gate voltage, output will be off. Okay. Similarly, if we are applying a low gate voltage or a minus gate voltage to the N side, it will be forward bias. Forward bias, that means low resistance. Low resistance means output will be, this transistor will be conducting. That means for low value it will be on. So low on. Okay. So in this way PMOS is working. So the CMOS is actually clubbing of both PMOS and NMOS. This arrangement. So this is PMOS, this is NMOS. Gates of both are combined and connected to the input. Okay. And this is the drains of both are shorted together, and for the output terminal, the source of PMOS is connected to high supply and source of NMOS is connected to ground supply. Okay. So let's now check how this gate is working. So this is a CMOS based inverter. That means if I apply A is equal to 0, then output must be 1, and if I apply A is 1, then output must be equal to 0. So let's say I apply 1 here. Okay. So if I apply 1, then both gates will be 1 1. Then I know that N type requires high gate voltage, so it must be on, and P type requires low gate voltage, so it must be off. So if this is off, this path cannot be established, but this path can be established. So that means V out can be connected to ground. That means for one input, for high input, I am getting a ground connection at the output. Okay, that's why output is 0. Similarly, if I apply a 0 here, if I apply a 0 here, then both the gates will be 0. Now P type will be on and N type will be off. That means this path will be prepared and this path will be broken. So in this case, if I apply a low voltage at the gate terminal, then my output will be connected to VCC. That's why I am showing 1 here. Okay. So in this way, I have prepared a CMOS inverter. Okay. So this is same thing which is written here. If I am applying a high voltage, then Q1 is off and Q2 is on, because their transistor, if it is off, then resistance will be high, if it is on, resistance will be very low, and in that case finally output is getting connected to ground. So that's why 0 is there. For 0 volt, Q1 will be on and Q2 will be off, so corresponding resistances are mentioned, and in that case my output will be connecting to VCC. So VCC, or we can say VDD, that means high voltage. So this VCC is actually denoted by VDD in case of MOSFETs. Okay, drain voltage. So this is the second case in which we have applied high voltage. So this is again the same connection, nothing else is there. We already covered this in the previous slide, both the cases, and this is the NAND gate now. If you want to cover the CMOS NAND gate, a NAND gate is found by modifying the base inverters. So NAND gate means Y is equal to A B complement. We have to realize this. That means A into B has to be realized. So this A into B, that means 2 NMOS in series, and corresponding to that 2 PMOS in parallel. Okay, so that's why we are saying 2 PMOS in parallel and 2 NMOS in series. So A, this is A, this is B. Similarly, this is A and this is B. Okay, simply we have connected to both these directions separately. Okay, now if I apply 0 0 here, so both are 0 0 0 0 and 0. So we can see that 0 is applied, that means P type is connected to the 0, that means P must be conducting, that means both these transistors must be on. So if this is on, then this prepares the path for this connection, that means output will be connected to VDD, and both these transistors will be off, that means there will be no ground connection. So that means I can say for this I will be getting a high or 1 output. Similarly for 0 1 and 1 0 as well, if any of the input is high, then one of these P transistor will be on. So if any of these P transistors are on, then there will be VDD path for the output. Okay, so in those cases also output will be high. But if both are high, then If both are high, that means they will be off, these two transistors will be off and both these transistors will be conducting. So, if both are high, okay, then this is the scenario. In that case, I can see that the output will be connected to this ground. Okay. So, this will be 0 or low. So, this is the CMOS NAND gate operation. Okay. Similarly, CMOS NOR gate is there. CMOS NOR gate means y is equal to a plus b complement. It is similar, that means a plus b, n in parallel and p in series. Okay. So, in that case, you can also check that if both these transistors are high, matlab if both these transistors are on, which is the only possibility if both are 0. So, for 0 0, both transistor will be on and it will be connected to VCC. So, for 0 0, I will be getting high output, and if any other situation is there, then I will be getting the low output. So, this is the CMOS NOR gate. So, these are the CMOS characteristics. Most widely used family for large devices, large scale devices, combines high speed with low power consumption. Okay, so usually operates from a single supply of 5 to 15 volt, excellent noise immunity. So, all these are plus, all these are positive points. So, can be connected to a large number of gates, about 50, many forms with propagation delay up to 1 nanosecond, power consumption depends on speed, perhaps 1 milliwatt. So, all these things are positive attributes of the CMOS family. Now, we have covered all three families. Now, let us compare them very quickly. So, basic gate offered by CMOS is NAND and NOR, TTL offers NAND, ECL offers me OR and NOR. Fan out, that means loading effect of the gate. So, 50, the output of a CMOS gate can be connected to 50 more inputs, and similarly this is 10 for TTL and 25 for ECL. Power per gate is 1 milliwatt and 1 to 22 milliwatt in TTL and 4 to 55. So, this is the highest power consumption and this is the lowest power consumption. Noise immunity excellent, very good. So, and propagation delay, it is the fastest, okay, and this is the slowest. But some special cases of CMOS are also there which can solve this speed problem. So, that is why we are mostly preferring between TTL and CMOS families. So, with this we come to the end of today's lecture. Thank you very much.